One tiny chip the size of a fingernail is the only thing standing between your phone and disaster. Right now, the lithium-ion battery inches from your hand holds enough chemical energy to ignite itself, and it would if a microscopic circuit wasn't making life or death decisions every second. Most people have never heard of it. Without it, your phone becomes a flamethrower, and the reason starts with the battery itself. Inside every smartphone is a packed reservoir of volatile chemical energy. The lithium-ion pouch cell is a marvel of engineering, packing immense power into a space as thin as a credit card. Inside, lithium ions constantly shuttle between a graphite anode and a metal oxide cathode, kept apart by a microscopic polymer separator. But this dense energy storage exists in a state of delicate, volatile balance. If the battery is pushed even slightly beyond its chemical limits, the system destabilizes. Overcharging forces lithium ions to gather on the surface of the anode, plating into highly reactive metallic lithium. Over time, this metal grows into microscopic, needle-like structures called dendrites. Like tiny glass shards, these dendrites can pierce the fragile separator, creating a direct bridge between the positive and negative terminals. This causes an internal short circuit. The stored electrical energy instantly converts into intense, localized heat. The same catastrophic failure can happen if the battery is physically punctured or crushed. Once the internal temperature of the cell crosses a threshold of about 150 degrees Celsius, the organic electrolyte liquid begins to break down. This decomposition releases oxygen and flammable gases, feeding a violent, self-sustaining loop. The hotter the battery gets, the faster the chemical reactions occur, releasing even more heat. This is thermal runaway, a self-accelerating chain reaction that cannot be stopped once it begins. The consequences are real and destructive. In 2016, manufacturing defects in the Samsung Galaxy Note 7 battery triggered this exact failure cascade, forcing a massive recall of 2.5 million devices worldwide. In the same era, a surge of hoverboards and e-cigarettes spontaneously ignited, leaving consumers with severe burns and causing millions of dollars in property damage. When lithium-ion chemistry turns on itself, the result is an instantaneous, white-hot blaze. Modern smartphones pack this volatile chemistry into impossibly tight spaces. Consumers demand devices that are thinner, lighter, and more powerful, forcing engineers to squeeze massive battery capacities into ultra-thin frames. This constant push for high energy density leaves virtually no physical margin for error. Inside a typical single-cell lithium pack, the layers of anode, cathode, and fragile polymer separators are compressed under immense mechanical pressure. In these tight confines, there is no room to dissipate excess heat. Even a minor drop, a slight bend in a pocket, or a microscopic manufacturing variance can compromise the structural integrity of the cell. The physical tolerances are so razor thin that any internal damage instantly threatens to trigger a catastrophic short, raising the stakes for every single charge cycle. To survive these razor-thin margins, every modern smartphone relies on a microscopic hero hidden inside the battery's safety stack. This is the Battery Protection Integrated Circuit, IC, a tiny mixed-signal silicon chip no larger than a single grain of sand. Operating entirely without user input, this silent guardian continuously watches the battery's behavior, carrying an outsized safety burden for billions of consumer devices worldwide. It acts as a security guard, a circuit breaker, and a high-precision thermostat, all combined into one microscopic brain, standing directly between daily convenience and catastrophic thermal runaway. Without it, the volatile chemistry of our devices would be completely untamed. But how does something so incredibly small monitor and control all of that power? The tiny chip makes 5 continuous, high-precision safety decisions to keep the battery stable. Inside its microscopic brain, 3 distinct roles run simultaneously: a vigilant security guard, a rapid circuit breaker, and a high-precision thermostat. First, the security guard monitors the incoming power. If the cell voltage climbs past a strict threshold of 4.30 volts, the chip instantly engages over-voltage protection. This halts the charging process, preventing the metallic lithium plating that causes internal shorts. Second, the chip prevents deep discharge. If the battery voltage drops too low, usually between 2.20 and 2.40 volts, under-voltage protection cuts the connection. This stops the copper inside the battery from dissolving and permanently ruining the cell. Third, the chip acts as a rapid circuit breaker. If an external short circuit occurs, current surges violently. The chip detects this current spike and shuts down the flow within 200 microseconds, long before thermal damage can start. Fourth, the chip continuously monitors heat through a thermistor input. If the temperature of the battery pack reaches 90 degrees Celsius, the thermostat commands an immediate safety shutdown. Finally, the chip executes these decisions through a pair of back-to-back MOSFET switches. Placed in series with the cell, these electronic gates serve as the physical disconnect path. When a fault is detected, the gates slam shut, isolating the battery cell and preventing a catastrophic runaway event before it can even begin. In 1995, a Nisshinbo engineer named Akihiko Fujiwara designed the RS5VG, the world's first commercial battery protection chip. This early design established a baseline of precision that modern engineers still rely on today. Today's silicon guardians, like the Seiko S8240, shrink that legacy down to a footprint barely larger than a speck of dust, yet they draw less than 2 microamps of standby current to keep from draining the battery. This trust is earned through brutal, standardized validation. Before any protection chip makes its way into a consumer phone, it must prove its reliability against rigorous global standards like IEC 62133 and IEEE 1725. In testing labs, these components undergo hours of thermal stress, long burn-in cycles, and extreme physical abuse. Engineers design these systems with redundant safety paths, ensuring that even if one component fails, a backup is ready to step in. It is this intense, repeated verification that gives engineers absolute confidence that this tiny sliver of silicon will perform its duty. This microscopic chip represents a highly sensitive line of defense, but it has absolute limits. Unsafe electrical conditions from counterfeit chargers can easily destroy the circuit. If the board is physically damaged or built with substandard components, the entire protection system can be bypassed. Extreme physical punctures or intense external heat can simply overwhelm the safety margins. When these guardrails fail, the breakdown starts small and escalates fast. Once thermal runaway begins inside the cell, the chip cannot reverse the chemical reactions. It can cut the electrical current, but it cannot rewrite chemistry. The chip is a safety switch, never an undo button. When these limits are crossed, the boundary between a useful tool and a dangerous fire disappears entirely. Preventing these failures on a global scale requires an incredibly precise industrial network. A single protection chip starts as a microscopic circuit printed onto silicon wafers inside advanced fabrication facilities in Taiwan and South Korea. These raw wafers travel to dedicated packaging plants in Singapore and Malaysia, where they are sliced, sealed, and run through high-speed functional tests. Only after passing these automated voltage checks do the microscopic components ship to assembly lines in China, where high-speed surface mount machines solder them onto battery circuit boards. This highly coordinated, multi-country supply chain operates at a scale of billions of units every year, converting highly volatile battery chemistry into a stable power source we can safely carry in our pockets. As we demand faster charging and thinner devices, the margin for safety shrinks. This microscopic guardian works tirelessly, but it requires us to choose quality accessories. The next time you plug in, respect the silent engineering keeping you safe. Subscribe for more untold tech stories.